Okay. So my talk is supposed to be some sort of seminar to the Professor Feigin's lecture. So there will be no new results in the talk, and everything will be rather old. And some part will largely intersect with his lectures. So be aware. I wrote some sort of abstract, and in abstract I wrote that I'm going to discuss two main examples, at least from the representative theory point of view of the shuffle algebras. One is a affine quantum SL2, and another is a toroidal algebra. What was it? I was told do not use it, just speak louder. And I still plan to do this. So I start from the quantum affine SL2. And since this is some sort of seminar talk, so please interrupt me if you have any questions, comments, find mistake. I expect there will be some mistakes. And there are different ways to define, at least three ways to define this quantum group. One is in sort of like RTT relation, the definition which works for any, another definition which works for any Kac-Moody algebra, the original different Jimbo definition. But for the shuffle business, the most appropriate definition is a so-called Negut-Drinfeld realization. I think it's still called new, but it's 30 years old. And in this definition, resembles the definition of SL2 of generators and relations. So we have, for ordinary SL2, we have E, we have F, and we have H. And here we will have generators of the same time, but with index, where n is integer. And relations looks like that. So it is convenient to organize these generators E into a current. So introduce E of Z is a sum of En Z in power minus n. Then the relations. So looks like that. This is a relation between E generators. Relation between E and H generators will have the following form. Is equal to Q in power H. Okay, to N. Okay, here put some gamma, which I forgot. Above we have also gamma, which is central. So there's not generally. And there are also more relations. So here I wrote quadratic relation in terms of E's. There is also quadratic relation for F. Is a function like this, but instead of Q we have Q inverse. And there is also relation how H commute with F. And there is also relation how commute E and F. And here we have some exponent of H times delta function of the form. Okay, let me write here variables. E of Z1, E of Z2. Here we have delta of Z1 over gamma Z2 plus another exponent. So I will not use precisely this relation, so I'm kind of sloppy here. You have any question?
Well, many.
Okay, let me finish formula and you'll have some chance. And the formula like that, where delta function, delta of z, is the sum of integer numbers z in power n.
There is minus n in the definition of current block, minus n minus 1.
Yes, in quantum cases, there is no notion of conformal dimension, so there is no shift.
Where is on this two blackboards, where is the word shuffle?
There is no word shuffle on the blackboard. It's my next point. But any questions so far? Maybe I already lost.
What these symbols in the second equation of this one? Yes, I cannot use
Q in power 2n minus Q in power minus 2n over Q minus Q inverse. This is Q number.
Okay.
And then some gamma.
And then gamma is the central generator.
And what is exponent of what in the lowest line?
Of something. Of H. Of some H with some coefficient. Some group-like element. H is some like Lie algebra element and exponent some group. Usually these exponents are denoted by something psi or k capital.
So this is series in one side.
This is, yes, but delta is a series on both sides. So on the right side we have all powers of z1 and z2. Maybe I want to comment about, for those who see it's the first time, about this notation for delta function. One of the this function have the following property.
I'm not so good at such stuff, but you commute E and E, yes? Not E with F.
Here E with F, yes. You are very good in such stuff. Question? One more mistake on the blackboard. Okay, the delta function has the following properties. That if I put delta on the z equal w, so this is an actual delta function for the delta function of the ratio. This actual delta function for on the diagonal where z equal to w, which is this can be expressed by the following properties: that delta of z over w times any, say, polynomial p of z is equal to delta of z over w times any polynomial, say, p of w. This is the property of delta. So if we multiply by delta function, we can change z or w and vice versa, whatever it will be convenient for us.
Are these relations sort of conformal series?
Conformal series, yes. So, for example, this relation in terms of components, if you substitute E of z in this way, this relation will take the form that commutator of Hn and Em is equal to En plus M with some coefficient, which is actually written here. And if you want, this relation is okay. Where is the razor? And this relation also can be written in components, and I hope I have a formula for it. I still hope, and probably it will be So this relation HE, this relation EE, so HE can be written in this form, and EE is just a 4-term relation. So we are trying to permute E and E. We cannot permute them just E and EM, but we can take a difference of 2 such consecutive terms, Q difference, and then we can permute this relation. Okay, maybe it's time to answer to the first question, where is a shuffle algebra? And from the first glance, shuffle algebra have a separate definition. So let me denote A by A, or actually A greater than 0 if you want to think, for some reason. And this is, as a space, this is a sum for L from 0 to infinity, the space of symmetric Laurent polynomials. And I will denote, of course, sometimes I will denote the corresponding term as AL. With the shuffle product, and I recall the definition, if I take 2 polynomials, one of L1 generators and another on L2 generator, then their product will be the polynomial on L1 plus L2 generators. And it will be symmetrization of just a product.
Excuse me, in the definition there is x1 when we start from L equals 0 summation. Then it's 1 or it's 0.
What is it?
In the C, x1.
X1 times XL. This is a comma dot.
Start from 1, not from 0.
From 1, yes. L equals 0, it is a polynomial of 0 variable, so this is just C, just constant. So here just recall the definition, and what is lambda? Lambda is so in principle this formula for shuffle product can be defined for any function lambda, and if time permits and I come to the toroidal case, it will be another function. But now lambda is a very concrete function. Lambda of x is a 1 minus qx over 1 minus x. So, as maybe in the first or no, better to say in the second lecture, Feigin said that by the definition, each term here is a rational function with the poles on the diagonal. But after symmetrization, there can be no simple poles on the diagonal. Therefore, it will be just a polynomial, symmetric polynomial. This is the definition. And the theorem, which I will state, and then if you try to write it left some space, I will correct it. That subalgebra of UQ of SL2 hat generated by all ENs for n is integer is isomorphic to shuffle algebra. I will not prove this theorem in full detail, but anyway, I will correct its statement to make it. Now it's not true, to be honest, and give some points. So just to understand why you can believe or have some reasons to believe. So first of all, we need to have some sort of correspondence. We need to assign.
Bologna says that we would have 4 different functions lambda, and here you say that we would only one, and we don't have the lambda for access from the same group. Yes?
For function, it was for SL3, for rank 2. I start and prepare my seminar tomorrow, so I don't know what he said. Don't ask me about his today's lecture. Yes. Okay. So, any other questions? In order to explain this theorem, we need to have some sort of correspondence between generators here and here. Generators are, just as I said, are En. Maybe I'll denote this subalgebra. Denote it by UQ of n hat. Here generators are En, and here we have, of course, big space, but as usual, this is what is this? It is the C plus polynomials in one variable, x, plus symmetric Laurent polynomials in one variable, plus symmetric polynomials on two variables, plus and so on. And of course, it is natural to take generators here. So we assign generators En to the x in power n. Where x in power n, I can put a bracket here, now considered as an element of the shuffle algebra. So the whole current E of z correspond to the sum x in power n, z in power minus n. Here I followed Feigin's notation, at least I try to do this, where he by reason denotes this variable in the shuffle algebra and variable in which we take current by different names, x and z. Here.
If we take not u but just u of n hat, then it is also shuffle algebra of the trivial lambda or
Yes.
just symmetric polynomials.
Yes.
Multiplication and symmetry.
Yes. Just commutative algebra. No, this is not immediately obvious from this relation, but you know, for SL2 heads, it's corresponding elements.
For 3 equal to 1, it's obvious.
From here.
I will comment about Q equal 1. Okay, so So I need to check relation. So I take the sum So this I'm calculating EE relations. And I want to show that the result is antisymmetric with respect to Z1 and Z2. If I permute Z1 and Z2, I get I change the sign. Now, you see, this is like a delta function. So multiplying this by Z1 is the same as multiplying this by X, by the property which I mentioned some time ago. So this is equal to the sum of n and m, z1 minus m, z2 minus m, and here will be x1 power n plus 1 product, okay, here without index, x in power m minus q, x in power n, product, x in power n plus 1. Now I need to use the definition of the product. So it will be sum z1 power minus n, z2 in power minus m, symmetrization of what? I take the this is an element of the shuffle algebra. So if I multiply x in power n plus 1 times x in power m, I don't get x in power n plus 1 by some element of the shuffle algebra, some polynomial of two variables. And by this definition, so I need to multiply. I write x, this will be symmetrization of x1 in power n plus 1, x2 in power m, minus q x1 in power n, x2 in power m, times, I don't know why I write it, okay, times lambda of x1 over x2. Okay? And we are almost done. So this will be the sum again by n and m. Symmetrization, z1 power n, z2 power m, minus. And symmetrization of what? Here, this I can write as a x1 power n, x2 power m, times x1 minus q, x2. And then I substitute my lambda and get x2 minus q x1 over x2 minus x1. And you see we get symmetric function here and antisymmetric here. And now it's easy to see that the result will be antisymmetric with respect to n. So the only, you see this non-trivial term 1 minus qx somehow is combined with this 1 minus q and getting the product symmetric function, which can be factored out from the symmetrization. So actually nothing depends on q now. So if we have, for example, I can say that if we had this relation for q equal 1, then we had it for general q. Nothing depends on q now.
Sorry, I misunderstood. So, but you originally have not commutative this. Suppose by is not originally.
Of course, it is not commutative, yes.
You make some deformation after the deformation is commutative.
No, it's not commutative. I'm checking the relation, and I'm saying that this relation doesn't, the fact that this relation holds doesn't depend on q. So it's only non-trivial term which we have in symmetrization can be factored out and cancelled. So we get quadratic relation freely. And it is easy to see that actually I almost do not use any properties of lambda. For any lambda, I can, for any lambda with shuffle, I can write the quadratic relation, but with the function lambda here. Like numerator of the lambda, something like that.
In the bread-last equality, you skip +1 and +1, yeah? Or is it x2 to the power of n +1?
Mm-hmm. Any other mistakes?
No, question. So what is the statement? You say that this symmetrization doesn't depend on utility.
Mm-hmm.
And that could be the argument.
Why doesn't it? Because this function which depends on q can be factored out. No, not the symmetrization. The fact that this symmetrization is antisymmetric with respect to n and m. I need to prove antisymmetry with respect to n and m.
So it's equal to 0?
No. Okay, so if maybe could make the argument clearer, but anyway, go further. Anybody can convince himself by his own arguments. So this is an explanation of the quadratic relations, but this is not the end of the proof. Let me explain what remains. So we have the following algebra. So first of all, we have our shuffle algebra A, which have the following which have first we have A0, which is C. Then we have, I denoted by V, the space of Laurent polynomials. Then we have space of symmetric polynomials, so this is actually symmetric square of V, and so on. It has the size of the symmetric algebra, and for q equal 1, this is PB. This should correspond to PBW theorem. For uq of n hat, we have C. Then we have a gradient which were called as X gradient in Feigin's lecture. So it's gradient by the number of e's. So we have C, then we have vector space generated by e's. This is again like V. Then we have some space generated by quadratic combination, and so on. And actually we have something, up to now, to be honest, we have something in between. We have something like A tilde, right? And this is a subalgebra generated by elements of the x in power n. And before I explained that we actually have a homomorphism from the quantum nilpotent to this subalgebra. And in order to prove theorem, we need to show that this homomorphism is surjective, this subalgebra is whole algebra, this homomorphism is injective, many things to prove.
So ADT is a tech, which is
yeah, it is. I will make some point about A tilde. But, to be honest, better to say that this is L, and so this is usually better objects. But we will see. Since we can. I want to compare the size of the algebras here and here. For shuffle algebra, size is clear. The size is the size of symmetric algebra. For the UQ and hat, one can prove that the basis here can be chosen in the form ei and j for e less than or equal to j. And further, if we have something e1, el, then one can choose a basis, or better to say, if you want, generators in the form such that e1 they're increasing. So therefore, the size of the U-curtain head cannot be larger than U greater. If I show that the A tilde coincides with U greater, then I'm done. Since this map is surjective, this algebra is generated by this EA, this algebra is generated by this its first component. This map is surjective. If this algebra has size non greater than this algebra, so if two algebras are coincide, then this map is also isomorphism. If A tilde greater is equal to A greater, then comparing sizes, we get an isomorphism. And about this statement, about this equality of A tilde and A, I have two remarks. If you want to use, one of them is good, and another, depends on your point of view, maybe. Okay, one. Assume that Q is the root of unity. Q in power k is equal to 1. Then we can consider algebra A. No, it will be actually then A tilde is contained in the algebra, which consists of polynomials, as before. Such that these polynomials satisfy which is so-called Will condition.
A tilde or
A tilde. Will condition, so this polynomial vanishes if we have here x1, qx1, so on q in power k minus 1 x1, and then other variables can be arbitrary. This is called wheel because we can arrange all these variables into the circle. x1, x2, so on, x3, and so on. Here's xk. And such that the ratio of two consecutive ones will be equal to q. The non-trivial statement is this is actually subalgebra. The space is subalgebra under the Cephal product. And the fact that A tilde is contained here is obvious because it contains if you have only one variable, if you consider generators like x in power n, then they definitely satisfy this condition because we cannot substitute will into polynomial one variable. So the non-trivial statement that these polynomials with this condition are closed under the shuffle multiplication, under the shuffle product. Why it is so? Take two polynomials, P1 and P2, which satisfy this Will condition, take their product, and then substitute Will inside this set of variables. Then either we will have all Will goes here and we get 0. Either we will get all Will goes here and we get 0. either we'll get two consecutive variables into lambda, and we get 0. The simplest example, if you want,
Now this is true only for such given lambda.
yes, everything is for this lambda. For another lambda will be another will. The simplest case, if you want that if q equal to -1, then this polynomial satisfies the following property, that p of x minus x is equal to 0. So if I substitute x and minus x here, either they both go to p1 and we get 0, either both go to p2 and get 0, either they both go to lambda, and in this case lambda of x is 1 plus x over 1 minus x, and we get 0 in the numerator. So for such q which is a root of unity, this map cannot be surjective, and actual theorem is not true. So for q is not actual theorem true for q is not root of unity. Any questions? Comments, mistakes? Okay, experts are sleeping. Okay, and the second, you see here I consider q root of unity, but non-trivial. I exclude q equal 1. Maybe it's time to consider q equal 1. And for q equal 1, shuffle product, the function lambda is equal to 1. So the shuffle product is just a product of polynomials and then symmetrization. So therefore it is more or less obvious that the whole algebra, that in this case, A tilde coincides with A. Any symmetric polynomial can be obtained by this procedure from the polynomials on one variable. So if I want to obtain symmetric polynomial, which is called same like m, I don't know, m mu. So which is symmetrization of x1 in power mu 1, and so on, xl in power mu l. Then this just by definition is a shuffle product of x1 in power mu 1, shuffle product x2 in power mu 2, xl in power mu l. So for q equal 1, A tilde coincides with A. Of course, this is just one point, but the fact that the algebra has big size holds an open set. So from this follows for generic Q, A tilde coincides with A. Because you see, I can take what holds for q equal 1. I take such products which are ordered, where mu1 and so on, mu l are ordered. Mu1 greater than or equal to mu2 and so on, greater than or equal to mu l, and say that they're linearly independent. We have a number of polynomials which coincide with the size of our space, and say that they are linearly independent. Of course, it's not true for any q. We have a counterexample for q of root of unity. But the fact that if they become linearly dependent means that some determinant will equal to 0. Some determinant vanishes. It will be some algebraic equation on q. And this equation cannot be just 0 equal to 0, because for q equal 1, this determinant is not vanishes. Therefore, if, for example, if q is not algebraic, is not root of any polynomial, then all the determinants will not vanish. And for generic q, we proved our theorem. So I'm not completely done, so I explained that for roots of units this theorem is not true, so and add this condition, and try to explain that for generic q, for example, for q is not algebraic, the theorem is true. Well, actually, it can be proven that the theorem is true for any q is not root of unity, but let me go further. I do not discuss it. Any questions? Okay. This theorem talks not about the whole algebra of Q of SL2 hat, but only about this subalgebra, UQ of n hat. One can ask how to get the whole affine quantum group. For example, one can ask how to have coproduct. If we say about quantum groups, we expect to have coproduct. And it is known that the subalgebra of Q n hat is not a Hopf subalgebra. It doesn't have coproduct. So if you try to write something like delta of E of z is equal to E of z times 1 plus 1 times E of z, like, since we don't have any other generators, and write delta of E of z2 in the same way, then delta will not satisfy the property of the homomorphism. So we have a quadratic relation that if we try to permute E and E, we have the function z over minus qz2 over z2 minus qz1. And if we try to permute these two products, these two summas permutes by this function, this also, but these two will just commute. So this delta is not, such delta is not a homomorphism. And there is a standard way to correct this. So this is bad. And instead of this, we write where K commutes with E by the following formula. This is lambda capital. After such definition, this coproduct is an algebra homomorphism. And probably I should write the coproduct, since I added K, I should write coproduct over K. And K is a group-like element. And K is a series in one direction. K of Z is a sum of some K, I don't know, Kn. Something like this. This is how the definition works for the quantum groups. So this relation which I wrote here is this I can write it as an AK relation. There's some replacement of EH relation. It's okay. There's some exponent of H like we had here. If I want to have definition in terms of shuffle algebra, this is a rule how this additional generators case commute with the generators like x in power n. Of course, it's better to have definition just in terms of shuffle algebra. For example, as I said, shuffle algebra, whole shuffle algebra can be generated not by its first component, by something larger and so on. And
is not a shuffle algebra, and if you want to make from its way the shuffle algebra, you have to replace the upper blackboard by something. What you just said?
I'm doing the standard steps. So here I get UQ, I already raised it. I had UQ of n hat. Now I embed UQ of n hat into UQ of b hat. Something like Borel subalgebra. And then the remaining step to UQ of whole SL2 hat is just Greenfield double. But already, in order to have Greenfield double, I need to have some Hopf algebra with product and comproduct. And also I need to specify pairing. And of course, I will discuss the Greenfield double, but I want to say how to get this UQ of B hat in something like shuffle algebra terms. I'm not saying, so more or less, I already said that I need to add additional generators which commutes with E like that. In terms of shuffle, this can be written in the formula that P, any polynomial P of x1, so xl, shuffle product which H of W is equal to H of W, shuffle product P of x1, so xl, product over A lambda of xa of W. Not HK. This in terms of shuffle algebra.
So you have to find a key which satisfies this relation.
I added. So I define the algebra Q greater than or equal as an algebra generated by A and this generator's Kn.
So key is not present in any kind of polynomial in X.
Yes. These additional operators which act on the polynomials morally by multiplying by symmetric polynomials. We have symmetric polynomials and we have additional operators acting on them, multiplication. We don't have, this multiplication is not shuffle product. And in this algebra we have, and this A greater than or equal is a Hopf algebra I can write formula for coproduct if you want, and if I have it. I have it. Delta of P of x1, so xl, is equal to sum for E from 0 to L, product for B greater than E H of xb, P of x1, xi, tensor xi plus 1, xl, over the product for A less than B, lambda of xp of xa. B, not that, A less than equal to E less than B. And so this is a statement, position. A greater than or equal to the Hopf algebra, and then we can take a trivial double of it.
What does it mean? So product of H's.
Yes. It means that we take P, our polynomial, then the symmetric polynomial, and we write it as the sum of a monomial. First of them, sum of the product of the monomial. First depends on x1 and so on xi, and the second depends on xi plus 1 and xl. And then instead of dot, we write tensor product. We need to, if you want, if you take just x in power n, compute delta. What do we get? We get this two terms, I equal to 0 and I equal to 1. And one of this term will be just 1 term times x in power n, and another will be h of x times x in power n, I think just like that.
H of xi?
There's no I.
Oh, in H, what is the argument in H?
XB.
Not any element of Schaff algebra. This Schaff algebra is symmetric polynomial. Yes.
Not in the algebra A greater than or equal, we have shuffle algebras and also, as I said, operators of multiplication.
As a vector space, this algebra is what?
This is a symmetric algebra on R matrix coproduct which we see from parallel realization nature. It is another.
Is your formula for coproduct of x to the power of n correct?
I think no.
Just what you written. In both terms, x to the power of n is in the right.
No, this is not correct. It will be first term. First term, of course, will be like this, but I think second term is not correct because it doesn't agree with formula which I wrote. But there will be some sum here, I think. I can erase it if you want. Another comment which I want to make is about this root of unity situation. You see here, if Q is a root of unity, we situation was the following. The algebras generated by our first generators is smaller than whole algebra. This is somehow do not fit the situation which we, from the first glance, which we have for quantum groups. In quantum groups, if Q is the root of unity, the quantum group have large center. Elements like E in power, in my notation K, belong to the center of the quantum group. So in the quantum group, we can take a subalgebra, take a quotient. We have a quotient algebra. We can take a quotient by the center. And here we have a subalgebra. And this somehow fits to the fact that this construction is not the construction of the quantum group honestly, but better to say the construction of the dual Hopf algebra to the quantum group. Okay, I don't have time to talk about toroidal algebra, but maybe if I stop here.
At the end, you almost reached the level of Feigin.
Okay.
So maybe you say we're an integrable system.
Integrable system lives in toroidal algebras. Okay. I think if I stop now, it will be better than anything else. Sorry.
Does anyone still have any questions?
A little question. What's the meaning of the sum between xi and xi plus 1 in the last?
There's no sum. This tensor product. It means that I take this polynomial, write all monomials in the form that first I have first axis from 1 to I, and then instead of dot, write tensor product in order to have element of the tensor product.
So that's